You know those huge life decisions like buying a house? So often, they come down to a gut feeling, right? It's all about emotion. But what if we could sprinkle in a little bit of cold, hard data? Today, we're going to look at how these simple yet really powerful algorithms, called linear models, can help us make sense of what might be the biggest financial decision of our lives. So, let's just get right to it with the big question. Could you really trust an algorithm to help you buy a house? I mean, it's a massive commitment. There are so many variables, so much uncertainty. We're going to find out if a model can actually cut through all that noise and find a clear signal.
To make this real, we're not just going to talk theory. We're diving into this really fascinating research paper where they took 2 decades of real estate data from Connecticut, and they used a pretty straightforward algorithm to see if it could actually tell you when and where to buy a home.
Okay, so how did they even get started? Well, before any algorithm can work its magic, you gotta have the right ingredients. The first step, and honestly probably the most important, is shaping all that raw data into something the model can actually sink its teeth into.
Think of this like a recipe with 5 clear steps. First, they looked at the big picture. They grabbed national mortgage rates for each year to get a feel for the whole economic climate. Then they zoomed way in, merging that info with specific property sales in Connecticut. To get even more local, they crunched the numbers for each town, and then, this is clever, they simulated a hypothetical mortgage to see what a real investment would have actually looked like. And finally, the most important step, they gave each scenario a simple label. Buy or don't buy. That right there, that's the answer key our model is going to learn from.
And this is a perfect way to visualize that merging process. A house price all by itself? It doesn't tell you the whole story. But a house price plus the interest rate when it was sold, now that is a much richer piece of information. Combining these 2 data sets is what really connects a single house sale to the bigger financial world around it. So after all that cleaning and combining and merging, this is what you get. This beautiful, clean, structured data set. This is the battlefield where our algorithm will be tested. Every single row is a summary for a specific town in a specific year. And that last column, buy recommendation, that's our target. That's what we're trying to predict. A simple 1 for, yep, good investment, or a 0 for, nope, bad idea.
All right, the data is ready to go. Now it's time to bring in our algorithm. We're going to see how a total classic, linear regression, actually holds up when you throw a messy, real-world problem at it, like predicting good real estate investments.
So what in the world is ordinary least squares, or OLS? Well, at its heart, it's just an algorithm trying to do one thing. Draw the single best straight line through a bunch of data points. Imagine a cloud of dots on a graph. OLS just wants to find the one line where the average distance from every single one of those dots to the line is as small as humanly or computerly possible. It's really just looking for the perfect average.
And this is the math behind it. Now don't worry, don't let the symbols freak you out. All this equation is really saying is, find the settings, that's the W, that make the difference between our model's predictions and the real answers as small as possible. The XW part is our best guess, and Y is the right answer. This formula just tells the computer, hey, make your guess as close to the right answer as you possibly can. That's it.
You know, what's really amazing is how easy this has all become. Using a super common tool called scikit, the researchers could set up and train this entire model in just 2 lines of code. It's just a perfect example of how these incredibly powerful machine learning tools are now totally practical for almost anyone to use. So how did it do? Well, here's the first report card. This is called the R-squared score. Just think of it like a percentage. A score of about 0.71 means our model could explain about 71% of what made a home a good or bad buy in the data it studied. For a first shot, that's actually pretty solid.
But this is the real test. It's like studying for an exam. That training score, that's how well you did on the practice questions you've already seen the answers to. The test score, though, that's the final exam with questions you've never seen before. A score of about 0.64 here is great news. It means our model didn't just memorize the answers. It actually learned the underlying patterns well enough to apply them to brand new data. And finally, we have the mean squared error. This number, about 0.09, basically tells us, on average, how wrong our predictions were. In this game, just like in golf, a lower number is always better. And this tells us that even when the model missed, it wasn't usually that far off the mark. It's a really solid level of accuracy. Okay, so our OLS model did pretty well. But let's be real, the world is rarely this neat and tidy. Now we're going to see what happens when our data gets a little bit messy and where a simple model like this can start to run into trouble. So, a really common headache in modeling is something called multicollinearity. It's just a fancy word for what happens when your inputs are related to each other. So, for example, when interest rates go up, home prices might tend to go down. This totally confuses the model. It has a hard time figuring out which one is really causing the change, and that can make its predictions get all wobbly and unstable.
Luckily, to fight this, we have some specialized tools. Think of ridge regression like a good manager. It sees two features that are kind of doing the same job, and it gently nudges both their influences down so they share the credit. Lasso regression, on the other hand, it's more like a ruthless editor. If it thinks a feature isn't adding anything to the story, it will just cut it out completely, shrinking its influence all the way down to zero.
So here's the key takeaway. We're not looking for one perfect model that rules them all. Instead, we're building a toolkit. OLS, Ridge, and Lasso, they're all specialized tools, and you pick the right one for the job at hand.
Let's take a closer look at Ridge. The way it fixes that instability problem from OLS is by adding a penalty. It basically says to the model, hey, look, I want you to find the best fit, but I also want you to keep the influence of all your inputs as small and simple as possible. This little rule makes the final model way more robust and less likely to get thrown off by those tangled up features in the data. And here's the formula for Ridge. See that extra little bit tacked on to the end? That's the penalty. The first part is the exact same as OLS, but that second part punishes the model if it tries to let any one input get too powerful. And that little alpha symbol? Think of it like a volume dial that we can turn up or down. A small alpha is a gentle penalty, but if we crank it way up, we're really telling the model to keep things simple.
And now for Lasso. Its superpower is creating what are called sparse models. By shrinking the influence of some inputs to exactly zero, it automatically does something called feature selection. And this is so useful. It doesn't just give you a prediction, it actually gives you an explanation. It tells you which factors really mattered and which ones were just noise.
The Lasso formula looks pretty similar, right? But look closely at that penalty term. It's different. It uses what's called the L1 norm, and that subtle little mathematical difference is what gives Lasso its unique all-or-nothing ability to just completely zero out some features. It makes it a fantastic tool for simplifying a really complex model. So let's wrap this up with our new toolkit. Think of it like this. Always start with OLS. It's your simple, powerful workhorse. If you're worried your features are all tangled up and correlated, grab Ridge to stabilize everything. If you think a lot of your inputs might just be junk and you want a clean house, Lasso is your go-to. And hey, if you want the best of both worlds, there's even a hybrid called ElasticNet that does both. We've seen that a pretty simple algorithm can give us a powerful, data-driven look at a decision as personal and complex as buying a house. But that brings us to the final, really important question, and it's for all of us. In a world with more and more powerful models, where do you draw the line between trusting the data and trusting your own human intuition?